So today's video is going to be on linear algebra and specifically Gaussian elimination. Now, if you haven't done linear algebra for a while or don't really understand matrices or matrix operations, I highly suggest going and giving the linear algebra course by 3 Blue 1 Brown on YouTube a watch. It's about 15 to 20 videos, about 15 to 20 minutes each, very bingeable, computationally light. It's mostly high level concepts. Really lets you visualize what is happening here. So I'm going to assume you're already familiar with matrices and matrix operations. And what I'm going to do in this video is basically go over the theory of the algorithm, basically how we're going to approach the problem, and then I'll release a follow-up video where we'll actually implement this algorithm in Fortran. Gaussian elimination is something that's done very commonly, especially in Fortran. It's something that you would definitely come across if you're doing the kind of things that people typically do in Fortran programs. So the whole idea behind Gaussian elimination is that, given some large set of equations, so we have some matrix A that's an n by n matrix, for n, say, greater than 3. So for small matrices like 2 by 2 or 3 by 3, you can use the Cramer's rule. It's typically like how people introduced to this for solving these systems of linear equations by hand. Typically, like, we don't solve these by hand for large equations. We use a computer, and that's mentioned, several times throughout the 3 Blue 1 Brown video series. And Gaussian elimination is the most common. So yeah, so for given some large set of equations, n greater than 3 for the number of unknowns, the idea behind this is we kind of develop a scheme to eliminate unknowns and then back substitute. So eliminate unknowns is the first step, and then back substitution is the second step. So the basic idea behind that is if we have a matrix, we've got A11, say A12, A13, A14, and then A22, A23, A24, A33, A34, and then A44. So if we have a matrix like this, and then we have x1, x2, x3, x4 equal to some, c1, c2, c3, c4, c1 through 4 are just constants. A1, all those A's are like actual values, like 1s, 2s, minus 10s, whatever. But if we have a system of equations like this, it should be fairly apparent that we can solve this, right? If we start here, A44, if we expand this out, we get A44 x4 equals c4, which lets us say that x4 equals c4 divided by A44, right? Like all these coefficients here are 0, which means x1, 2, and 3, they're all 0. This is very easy to solve. And then once we've got once we know A4, we can plug that, sorry, not A4. Once we know X4, we can plug that into this second row here. So we'll get A33X3 plus A34X4 equals C3. We know this value here. We can substitute that in. We get, A33X3 plus some constant equals some other constant. We rearrange, we divide again, and then we know X3. And we basically just keep working our way up this matrix. So given this a matrix in this form, so this is it's called upper triangular form because you'll notice there is like a triangle of zeros here, and then we have this upper triangle of values. So this is called upper triangular form. If we have a matrix in this form, we can solve this system of linear equations. So this is the whole idea. So this is kind of the idea of back substitution. The first step forward elimination is basically how we get our matrix into this form. So the idea of forward elimination is, so let's say we have a matrix. I'm actually going to write what's called an augmented matrix. Hopefully you're familiar with that. Basically, it's just a shorthand of writing what we saw on the previous page. So I don't know, let's pick some values. Something like this, 0, 3, minus 2. So this would be our matrix of A's. We're just going to do a line here. And these numbers to the right of the line are basically our C values. So we can write the matrix like this. This is called an augmented matrix. If we go back here, those A values are kind of this. And then these constants here is this column here. It's just a shorthand way, so we don't have to write, you know, the x1 through to xn equals c. Like this is just a compact way to describe our matrix in a way that lets us do operations on it while preserving all the, you know, laws of matrix operations. So we're going to do what's called row reduction on this. Now, row reduction is basically some things we can do to this matrix that, you know, make the system of equations hold. So we can swap the order of any of these. So we can swap any rows, and this without changing the system. Like this matrix is arbitrarily arranged. These are essentially 3 separate equations. We've just put them this way in the matrix. As long as we're including this, you know, value of C, or this right hand side of the augmented matrix when we swap, we can't just swap these A values around. But if we swap the entire matrix, that's completely fine. We can multiply by a constant coefficient. It has to be a non-zero. Hopefully that should be obvious, but when we're talking about like scalars, just any non-zero scalar, if we multiply an entire row, it doesn't change the outcome. This is exactly the same as if you had, you know, like an equation like ax plus b equals c. You can multiply everything by 2, and that still holds. Like that is a pretty intuitive and well-known property of linear equations. And then the third one, which may be like less intuitive, is we can add any 2 rows. So you can imagine, so, you know, we can add row 1 and row 2 together. So we can make, you know, like row 2 is equal to row 2 plus row 1. And this also doesn't change the underlying system of equations. Now you can think of this as like, you know, if we go to ax plus b equals c, back to this example, you know, we could add 10 to both sides, right? Ax plus b plus 10 equals c plus 10. We're just adding 10 to both sides, it cancels out. It's essentially the same thing, right? We can just add, instead of 10 here, we can add any arbitrary equation to both sides, and that'll work. So that's essentially where that's coming from. So we use these properties of row transformations to help us get this augmented matrix in the right form. So for this example, I'm just going to do a few steps. I'm going to step through all of this, but essentially we want to make our matrix look like all these zeros here. So the first thing I'm going to do is actually get like row 1 to have just a 1 in that top left corner. Now the reason I'm going to do this, so I'm going to go row 1, I'm going to multiply everything by half, by 1 on 2. So that'll give us row 1 is going to equal to 1 minus 1, 0, minus 3, right? So we can rewrite our matrix as 1, minus 1, 0, minus 3, and then 1, minus 1, 1, 1, 0, 3, minus 2, minus 5. So that's our new matrix. And then I'm going to use this add any 2 rows rule. And if I want this R2 to have a 0 at the start, I can do a R2 equals row 2 minus row 1. You can think of this as like a plus, negative 1, lots of row 1. It's fine, it's the same thing. Add or subtract rows, doesn't matter. So we're essentially just going to do that. So I might just do this in a separate color next to it, just for visibility. So we're going to minus row 1, so 1 minus 1 becomes 0, minus 1 becomes negative 2, and 1 minus 0 stays 1, 1 minus 3 becomes 4. So our R2 then goes to 0, minus 2, 1, 4, which gives us a new matrix. Let me go back to this. So 1, minus 1, 0, 0, minus 2, 1, 0, 3, minus 2. And then the right hand side of this is going to be minus 3, 4, minus 5. Alright, so now we've got those zeros all good. Perfect. The next thing we want to do is to get this to 0, right? Repeat the process. We multiply row 2 by some scalar, we subtract that from row 3, and we carry that through until that gets to 0, and then we're done. This is a 3 by 3 matrix. We only need to get to get these to 0, and we're done, because this is our last unknown, and this value here will be the last one. So that's basically the idea. I won't like compute everything here, because we might as well let a computer do that, and that's what we'll do next time. Some notes though, things to look out for when we do this. So as n grows, this is going to be, as n approaches infinity, or as it grows, this is going to become like computationally expensive. There's a lot of operations we need to do as n grows within each row, and the number of rows increases. But we also need to be careful for division by 0. If we go back to this example here, if we had have chosen a matrix where this value here somehow ended up to 0 after the first lot of row reduction, or was already 0, we're kind of stuck, right? Because this 3, if this -2 is a 0, there are absolutely no row reductions possible to cancel out that 3. So we get stuck. And the solution to that is something called partial pivoting. And you may already be able to see a solution to that based on the rules. We can swap any 2 rows. So if we get into a scenario where one of our pivot entries is a 0, we just swap it with a row that has a non-zero entry. So if that was a 0, we would just swap these 2 rows around, and would be good, because that 0 would move down here, which would be great. Would have a non-zero on the diagonal, would be great. So that's all you have to do. You just have to keep an eye out for division by 0. So there's a technique called partial pivoting, and the idea behind that is before you do your row operations after each row. So once you've got your first 0, or even before you start, you essentially put the largest. You look down the whole column n. So the first iteration, you look in the first column, and you take the maximum of the absolute value of I1. So basically whatever the biggest absolute value in this column is, you make the top entry, and that just always avoids the division by 0 issue. And then the last one is round off errors. So if you're not dealing with nice integers here, and you've got floats, which is often the case, you can see like just the sheer number of operations we do to every single entry in this matrix, round off errors accumulate. So you want to use double precision. Use a high level of precision so that those round off errors don't become a thing. Now partial pivoting isn't a complete solution to division by 0, but if you hit a division by 0 case while using partial pivoting, it just means that your matrix is not invertible, which means there's infinite solutions. So it's not necessarily a limitation of the algorithm, it's a limitation of the system of equations you're trying to solve. So conceptually, it's very easy to understand. We already went through it, but you feel just more generally, you kind of have this an-1 to the xn-1 plus an xn equals c. This is what we had all the way back here. We did that swap. So if we start at this point, you rearrange to get xn-1 equals c minus an xn all over an-1. And if you repeat that, you eventually get kind of like the general form of, xi is going to equal to 1 over aii by ci minus the sum from j equals I plus 1 to n of aij xj. And this is for I equal n-1, n-2, all the way to 1. And this aii, this kind of notation here, just goes back to the original matrix notation. Yeah, right. So that's the general solution for back substitution. Like when you're computing this, you can basically compute xi in this way. Yeah, and that's essentially the algorithm that we're going to implement. So hopefully this makes sense. We'll put this into code in the next video. Should really clarify it even more. And yeah, that's it.